here we are at the physics video lecture, Physics 203, video lecture 15. We are talking about phase space, Hamiltonian mechanics and phase space. So I have a couple more interesting applications and examples for starters. So let's review. Phase space is the two n-dimensional set of coordinates and momenta. The thing with the Hamiltonian mechanics is that the coordinates and the momenta go into the system, into the equations of motion, into the dynamics equally, equivalently. We'll see later when we do canonical transformations, you can just change the names of these things and everything still stays the same. Good, so we have this two n-dimensional space. And a point in that phase space, of course we can only draw it like this, Q and P. A point in that phase space represents a state of the dynamical system. So if you have these n degrees of freedom, a point in the two n-dimensional phase space gives you the state of the system in terms of, you know, its coordinates and you know the momenta at that point in phase space. Okay. The example we looked at was the simple harmonic oscillator, where we had H is equal to P squared over 2m plus 1/2 k Q squared. So there's a simple harmonic oscillator. And Hamilton's equations, we can write this way. E dt, the vector QP, remember we have Q dot P dot, and that vector is dH dt, and oops, not so fast. This one gets the minus sign dH dq. So this is a vector, the time derivative of the vector, and this is a vector, obviously. This is also an equal sign. It's a function of Q's and P's. So the Hamilton equations generate a vector field. They represent a vector field, and for the harmonic oscillator, we saw that the momentary velocity, right? This is the velocity vector of a phase point, is given by this vector right here. And therefore, if you draw enough of these, you'll actually get the phase curve. And for the harmonic oscillator, it goes around here clockwise. I'm going to continue with an extension of this. And I should say also, for different values of H, which is the energy, you'll have different curves here. These are just smaller amplitude, smaller energy solutions to this. They're all going clockwise. And in fact, the very center here, the origin, represents an equilibrium point, a stable equilibrium, because that's the harmonic oscillator. So all I'm going to put here as a note, we've got a stable equilibrium at the origin. That's for our harmonic oscillator. Got a stable equilibrium at the origin. Okay, so these phase curves is what we can call these here, are never going to cross. So there are certain properties here. Phase curves do not intersect. That's a property here. And that's simply because if two phase curves were to intersect, you'd have one point which represents an initial condition with two possible motions, okay? So for that reason, phase curves do not intersect, and the reason here is uniqueness. Unique solutions. differential equations. See, if you had a phase, if you were out here in phase space, and you had a point where two phase curves intersect, then those solutions to differential equation would not be unique. Good, so I'll put a star right there. Okay, the extension of this, and we're going to address unstable equilibrium next. So the extension of this example is going to be a pendulum on a rigid rod that can rotate the full 360 degrees. So our next example, we'll take a pendulum. See if we can fit the full analysis on this board here. So we'll start over here. So this time the pendulum can rotate. So we've got the angle phi, ML. This is a rigid rod, so we can go the full circle if we need to. Okay, we go around in a full circle, and we need the Hamiltonian, Hamilton's equations, and so forth. Okay, so how about the Hamiltonian? H is equal to, here, let's start this one from scratch. It's not exactly the same. It'd be very similar to that. Start this one from scratch. So we have L equals 1/2 mL squared phi dot squared. That's the kinetic energy minus mgl. I can write 1 minus cos phi. I could have also just written negative cos phi. Okay, 1 minus cos phi. Which way is better? Let's just do the minus. For simplicity, minus negative mgl cos phi. I may change my mind again. Okay. So what about the Hamiltonian? Now, p sub phi is equal to dl d phi dot. So what we're going to do first is we can write the Hamiltonian just as the sum of kinetic plus potential in this simple type of case. So we have 1/2 mL squared p dot squared plus negative mgl cos phi. And now remember, we have to make that substitution. And this was mL squared p dot. So we substitute, we have 1/2. The phi dot is p sub phi over mL squared. So we'll have p sub phi squared 2 mL squared. I'll go ahead and write it like that. Plus negative mgl cos phi. So there's our Hamiltonian in P and phi. And what we want to get is the phase curves here. It's not all going to fit on one board. That's just the way it goes. MGL cos phi. Okay. Now, so next, phase curves. So for small phi, then of course we can get the small oscillations Hamiltonian, if you want to call it that. Small phi, we have cosine of phi is equal to 1 minus phi squared over 2. Yeah, I see, that's why I wanted to have the 1 in here. Yeah, let's do this. Minus, okay, I'm going to correct this just to be systematic about it. That way, if you haven't really mastered this yet, you're seeing it now, okay? Make sure you see where this came from, MGL 1 minus cos phi. But now when I do my expansion, cosine phi is 1 minus phi squared over 2. So I'm not changing the name of the Hamiltonian each time. So the small oscillations version, we've got p sub phi squared over 2, I got the 2 there, over ml squared plus mgl phi squared over 2, so plus 1/2 mgl phi squared. This, of course, is identical to this one up here, up to a couple different letters. And so the phase portrait, and should I go away from P? Yeah, so I'm using phi now. Okay, so phi, P sub phi. It's just like the harmonic oscillator. But that's only for the small angle approximation. What happens when the angle is larger? After all, we're going to allow this angle to be all the way up here, pi. Okay. What happens when the angle is larger? And right now what I've drawn, of course, is what I'm just erasing here. Stable equilibrium at the bottom of the pendulum. And the angle is close to 0. And I just get these ellipses here, ovals, whatever you want to call them. Actually, they're ellipses for the time being. Now for larger, so number 2 here. For larger angles, what happens when the angle is larger here? We're back to this. You can go to 1 minus cosine of pi, and that's 1 minus negative 1, you get 2 times mgl. For larger angles, let's go ahead and draw the phase portrait like this. So pi is apparently an important angle. This graph you want to make pretty large, okay? 2 pi minus 2 pi. So for small angles, and this is phi sub phi. For small angles, we saw we had this. Now let's solve for p sub phi as a function of phi for the larger ones here. So for larger angles, p sub phi is equal to 2ml squared. You're going to have h minus mgl 1 minus cosine of phi. It's going to be a square root here, and a plus minus. Let's make that cleaner, but otherwise it's true. So we're going to have plus minus 2ml squared h minus mgl plus phi. You got to ponder this for a moment. What is the value of the energy we're talking about here? Energy would be at maximum amplitude, okay? Maximum amplitude when the momentum is 0. So when this thing vanishes here, we have h is equal to mgl 1 minus cosine of pi, which is equal to 2mgl. So we get this this expression right here, the red star. So we have 2 mgl minus mgl plus mgl cos phi. So H is equal to, no, not H is equal to this expression star is going to be equal to mgl plus, right, we have 2 mgl minus mgl plus times 1 plus cosine of phi. So piece of phi is equal to plus minus 2ml squared mgl 1 plus cos phi. And of course, this is the important part. We just have constants there. So piece of phi vanishes when cosine phi is equal to pi. Okay? It has a maximum when cosine phi is equal to 0. So what's happening here, it's no longer an ellipse, but it's got some maximum value and it goes down to here. It's symmetric, and it's got the minus sign, goes to here. Okay. So this is the phase curve for the energy in which the pendulum is very close to just standing on its head. Okay, it's standing right here. In fact, this one separates two principally different types of behavior. So inside here we have stable equilibria, and we have these clockwise ellipses and ovals. This particular energy is really right there unless you give it a little push. Okay. So if you give this thing a little push, you're going to be, actually before talking about giving a little push, now you notice I've got 2 pi and minus 2 pi. Well, if we just turn this pendulum around one time, we're just repeating ourselves over here. Okay. So the stable equilibria are 0, 2 pi, minus 2 pi, 4 pi, etc. Okay. The unstable equilibria are pi and negative pi. You could say 3 pi and negative 3 pi. And suppose we now give this thing so much energy that it just rotates. Okay, so much energy that it just rotates clockwise or counterclockwise, it doesn't matter. Okay, let's have it rotate. In fact, we'll have it rotate counterclockwise for the moment. Okay. Then what that represents is an energy that's a bit larger, and the thing never comes to an exact stop. So it's going to go like that. And the phase curve, poorly drawn, but you get the idea. Okay, it's supposed to be smooth over the top right here. And then you can see that in the other direction, clockwise, it's really the same thing, except like that. So that's a rotating, that's the phase portrait for a rotating pendulum, rotating pendulum. These are the stable equilibria. I'll go ahead and make them red. Stable equilibria. And these here are the unstable equilibria. Okay, unstable, exclamation point. So what is the nature of an unstable equilibrium? Well, you can see this here is the limit of a clockwise oval, no longer an ellipse. And this here would also be the limit of a clockwise oval, because you're just over 2 pi, or pi. And that means the nature of An unstable equilibrium is a vector field that is diverging. Notice we have arrows coming in and arrows going out. Good, yeah, so this analysis is pretty great. So I'm going to write one more time. Stable, you have this kind of a phase portrait, and unstable, you have this kind here, vectors going and coming, okay? I can do that one a little better. It's just that point where they're coming in and leaving, going in and leaving. Check the directions on these things. You'll notice that is truly a different geometrical property of a vector field. So a stable equilibrium is characterized by this. How about we make the equilibrium points red? Got that option. Okay, totally different behavior of those vector fields. So Hamiltonian mechanics is actually geometry in the phase space in this regard. Okay. So next example, this was an important one. You can do a better picture of that maybe. Good, let's see what else we're going to do here. I have a bunch of examples here in my notes. Let's do the phase space of a simple one-dimensional free fall. So phase space for one-dimensional free fall. So what do we have? We can actually cut to the chase here. Hamiltonian is p squared 2m, so single particle one-dimensional free fall. P squared over 2m plus mgq. I'll stick with q. Okay, q is the vertical axis, the up direction, mgq. So for a given energy, we can solve for p. So P equals plus minus the square root of 2m. I'll label H the energy, E minus mgq. So let's graph that. P of Q. Q and P, good. So when mgq is equal to E, that's the maximum value here of, not of P, but of Q, okay? Because we're under the, so I'll write Q sub max, and Q max is equal to E over mg. It's right there. And this graph is just something like this. It's a parabola on its side with a square root. And for any energy, this would be a certain maximum energy in the phase curve, you think being launched and falling back down like that. I want to do a second version of this one. One-dimensional free fall with a bounce. So things can only rise and fall, say as high as the ceiling or something. Good, so let's label as 1. And oh, before I go on, for smaller values of the energy, we would have this, okay? This would be a certain value of the energy, smaller values. So there's our phase space. Now let's do the one in the bounds. Yeah, and we'll do it right under this one. So what we're going to do is let free fall with a bounce at Q equals 0. The origin on the floor, we have an ideal ball that can just bounce up and down, no losses. So now we have H equals P squared over 2M plus MGQ, and now I'm going to add some constant times delta of Q. This is just to forbid the thing from going down into negative Q territory. You know, here we could actually have some elastic potential over a small, thin layer in which things bounce ideally or something. So we're just gonna, here I'll just call this elastic bounce. Because we're not concerned with its exact form, okay? So what does the phase space look like this time? So we still actually have the same P of Q plus minus the square root of 2M E minus MGQ, with Q is restricted to being greater than 0. I'll even say greater than equal to 0. How about greater than 0? Okay. That's the restriction that this delta function, elastic bounce, does. And now the phase space, the phase portrait, is going to look like this. Because we're just graphing this thing here. We still have our maximum for a given E, E over mg. And we still have these parabolas on their side like that. But what represents the bounce is that it comes into contact here. There's a really thin elastic layer, and it's going to go back up to here. And for a smaller energy, we would have the same thing. So those are the phase curves. You notice they're still always going to be clockwise, and that bounce just means that we have a very, think about it, what it means. You've got some really strong force there, some really strong gradient, and you have some really large vectors that go from here up to there again. Okay, so there's another example of a phase space. This is good too. The previous one is really important though, with the stable equilibria, stable and unstable equilibria. Okay, good. So now I want to discuss some properties of these phase flows. So I need to define the phase flow. And in fact, what I've been showing you is the phase flow. So I just have to give it a reasonable definition. The idea is that we've got our phase space, Q and P, and we've got a point here, and we know that this point can be thought of as Q0, P0. We can think of it as an initial condition, and as such, it's the initial condition to the solution of the differential equation. Q0 is the initial condition to the solution Q of t, P of t. Okay. I'll write vectors row or column interchangeably, whatever suits us. Okay. So it's the initial condition to this solution, and we refer to this solution as the phase flow, because we have a bunch of phase points in this phase space, and if you take any one of them, the solution takes that point along a path, along the trajectory. So we call that the phase flow. And the idea is that we can have a little region of initial conditions, and then the solution would take that region of initial conditions on a little journey, so to speak, okay? So the points in the phase space are the phase fluid, and the solution of the differential equation, Hamilton's equations, is an operator that takes that region around through phase space. So there's our phase flow. Let's see how I define that here. That's good enough. Yeah. Phase flow. Here, I'll define it. I'm just going to call it the transformation that maps Q sub 0, P sub 0 onto Q of T, P of T. It's another way of looking at things. Okay. So there's a really important theorem now that says that this region of phase space that's defined, a collection of initial conditions, will retain its volume in phase space as the transformation carries it along. So this theorem is called, here I'll start a new board, UVA's theorem. I'll spell it. If someone knows French, they can correct me. UVA, Louisville, is a U, V-I-L, UVA's theorem. Phase flow preserves volume. That's a nice short way to for our example, the harmonic oscillator, because we own that thing. So let's imagine we've got the harmonic oscillator, Q and P, H equals P squared over 2M plus 1/2 K Q squared. And we know for a given energy, we have these curves, okay? And let's just take an initial condition over here, or a collection of initial conditions. So that's the whole region in phase space corresponding to different energies, right? And the phase flow is going to carry this whole thing around. In fact, it's going to be carried around and land right back on itself because we have a perfectly periodic motion. Saying that it preserves volume means that as it goes around, over here, it's going to be more stretched out, and over here, right, because this is a compressed, it's an ellipse, not a circle. Over here, it's going to be exactly the same shape it was here, right? And over here it's going to be more stretched out. But notwithstanding that, the volume, that is to say in two space, the area, but generally the volume of this region is going to always be the same as it's carried around by the phase flow, which is carrying it around clockwise. So the phase flow preserves volume. Now what we're going to see is this is just the property of Hamiltonian systems. That's what we're working with. And the proof is going to depend upon the incompressibility of a flow in fluid mechanics. So I'm going to give that proof now, but we're going to get to fluid mechanics in the end of the semester. Not that far off. We're going to get to fluid mechanics, and then I'll give the full rigorous proof, but I'll show you what it depends on. So the proof. We have H equals H of Q1 to Qn, P1 to Pn. No time dependence, energy is conserved. That's the kind of system we're talking about. Now, consider the velocity field, is what we're going to call it. Q1, well, let's go ahead and do this. Q1 to Qn, P1 to Pn. And as we know, that is these two gradients, dH dP minus dH dQ. Actually, since I'm writing them explicitly here, I have to have, so for Q1 to Qn, I have my dH dP1 all the way down to dH dPn, and then I have minus dH dQ1 down to minus dH dQn. So this is a velocity field, and to show that it's incompressible, right, or to show that it preserves volume, I have to show that it's an incompressible velocity field. The velocity vector is incompressible when its divergence vanishes. Now that's something I'm going to prove to you guys later, because we'll talk about this in fluid mechanics. Right now it's a formal thing. So if the divergence of these vectors, which are identical, right? If the divergence vanishes, then the velocity field is incompressible. So down here we'll write proof later of this statement, but that the divergence of this vanishes, I can show right away. Divergence of a vector A1 of x all the way down to AN of x. The divergence of this vector, in fact, I should have started with, let's do this. So the divergence of a vector is equal to the divergence of, I'm just writing out the components, okay. what is that? That is the sum of the dA sub I dx sub I equals 1 to n. That's how the divergence is always defined for our system over here. We have two kinds of variables. You have q1 to qn and p1 to pn, but that's a 2n variable vector. Okay? 2n component vector. We have divergence of q1 dot all the way down to pn dot. I'll write that in shorter form. That's going to be two sums. We're going to have I equals 1 to n dqi dot dqi plus there's the next sum is going to be dpi dot pi, and let's see what we get. Qi dot is dh dpi, right? Qi dot. So remember, they're all dotted in here. So what we're actually having is d squared h dqi pi equals 1 to n over here, and here we're going to have the sum over negative d squared h dpi dqi. Yeah. There we go. dpi dqi. And you'll see that these are the same as these over here. We're going to assume we can flip the order of differentiation with a minus sign, so that equals 0. So the divergence vanishes. I'll show later how that gives us incompressibility. I actually have a really beautiful, much longer proof, but I think it's worth it to give this short one because this is the whole formal property that makes it happen in whatever proof you use. And then since we're going to do fluid mechanics later on, we'll get that for an actual fluid, and we'll see where it all comes from. Okay. So proof later, and let's even put this in our notes here. Proof later, fluid mechanics. Yeah, I really am going to leave enough time for the fluid mechanics because we're going to tie things together really nicely in the entire subject that we're doing. Right now we're right in the middle, we've got a lot left to do. So we have the incompressibility of the phase flow. So again, that's a formal property of Hamiltonian mechanics. This phase flow represents the fact that we've got a vector field there, and the incompressibility is a certain property of that vector field. So the mechanics is geometry on the phase space, as exemplified by those stable and unstable equilibrium points. Now let's see how we're doing time-wise. Okay. So I can say a little bit more about Hamiltonian systems now. This would be a great way to wrap things up and keep talking about the phase space. So good, incompressible. Okay, let's call this next thing phase space. Volumes volumes in phase space. Volumes in phase space. my example I want to use is an ideal gas. So suppose we have an ideal gas with n particles. Probably use capital N particles. And what we want to do is rough in the idea of the phase space here. I think I have some decent notes on this. Proof. Yeah, here we go. N particles in a box L cubed. So we have a cube size L. Okay, it's got gas particles in it, ideal gas particles, a whole bunch of them. Okay. So what is the phase space of a system like that? Let's take it a step at a time. So the energy E is just going to be the sum of p sub I squared over 2m sub I. And let's just let the particles be identical. P sub I squared over 2m plus u. But since these are free particles, except when they occasionally collide with each other or collide with the side of the box, this u is essentially equal to 0, except for a bunch of delta functions, okay? So, since it's an ideal gas, just 0, like that, for starters, okay? So, we have, I'm going to just use the formulas for the ideal gas. We have 3/2 N K Boltzmann. Temperature, 3N P squared, P squared root mean squared over 2m like that. And we're going to call the volume in phase space volume V sub P, okay? What about volume V sub Q? So V is going to be V sub P times V sub Q, okay? So V sub P is going to be constant regardless of as long as it's an ideal gas, regardless of the size of this box, okay? That's not going to change the energy in there. So that's just V sub P. What about V sub Q? Well, V sub Q is is a volume for every degree of freedom, since they're independent degrees of freedom. So actually I could leave the V sub P here, and then for each individual degree of freedom, we've got L cubed, okay? So we've got L to the 3 times N. So we'll just put a box around here. This one we're not concerned with treating as a constant, but L to the 3N. So that's ideal gas with N particles in a box, L cubed. What if we have the same number of particles in the box that's just been split in half, okay? So next, what is the volume and phase space for the N particles in 1/2 of the box? Question mark. So we can say in the right half of that box, put them all on the right side. Question mark. V sub 1/2 is going to be the same V sub P for all practical purposes. And then we're going to have one of those L's, so we're going to have L to the 2n times L over 2 to the n. Okay. So V sub 1/2 is going to be 1/2 to the nth power of the original V. And remember, n is a large number if you have gas particles in a box. So that volume of phase space is just infinitesimal compared to the original volume of phase space. And suppose we said, okay, not in the left half, but in a corner of the box, it is L over 2 on each side. V sub, I'm going to say 1/2 corner is going to be 1/2 to the 3n power times velocity. And if you wanted to just have all those particles confined in a small corner, you can see these volumes are absolutely infinitesimal. You take 1/2 to the nth power, where n is 10, 20, 30, 100, etc. This is an extraordinarily small corner of the entire space. Okay. So that gives you an idea of the relative volumes of phase space. When they use phase space in statistical mechanics, these relative volumes are interpreted as probabilities. And then you can say the probability for all the particles in this gas to somehow all be found in the right side of the box is going to be 1/2 to the number of the number of particles in that box. So, you know, if it's a liter or a cubic meter, there are 10 to the 23rd particles. For them all to find themselves in one side of the box is this extraordinarily small number. So that's where you're going to use phase space when you go into statistical mechanics, and you want to have this in mind because, you know, it may not be presented to you this explicitly, or it'll just be assumed that you recognize that. Okay, so I'm just going to put here applications in statistical mechanics, so when you encounter them, you'll know where it's coming from. Applications in statistical mechanics. And so the idea of the phase space is really important. And often these discussions of probability are just, they'll run through them really fast. But really concrete example here. So should we label this anymore before we move on? So this is the volume in phase space for the n particles if they're in 1/2 of the box. Okay. So it's 1/2 to the n, so that's the answer to that. And if you put them in a corner of the box, like I said, it just gets smaller and smaller. These numbers to a power of any large n are utterly infinitesimal. Okay. I have one more. I'll leave it right there for now, okay? Next time we're going to do Poisson brackets, and we'll see you then. So,